is a PhD fellow at Chennai Mathematical Institute and also a visiting research scholar at IIT Kanpur, and is almost done with his PhD at IIT Kanpur and CMI under the supervision of Nitin Saxena. So he has some stellar results during his PhD, and he's going to present one of his results.
Yeah. Yeah. Thanks, Surajit, for the invitation. Yeah. So hi everyone. I guess I think you can't see my face and I can't see your face, but it will be a journey, I guess. So today I'll be talking about border depth 3 algebraic circuits. So what I plan is to really give a, a brief overview of GCT and our result. I'll not really get into technicalities and proofs and so on. And but yeah, so I'll try to give some flavor of the sort of GCT works that I have done and what are the results we have proved and what are the results one could achieve using algebraic techniques and not geometry methods. So yeah, and hopefully towards the end or at the end of this talk, you'll learn something or you'll take away something from this talk. So yeah, so this is a joint work with Pratik and Nitin. So let's start. So these are the four sort of themes that I'm going to talk. Just for the introduction, I'll give some basic definitions from algebraic complexity theory. And then from algebraic complexity theory, I'll build up the notions in GCT, geometric complexity theory and border complexity. And then I'll specifically talk about depth 3 circuits and its border and our results. And then I'll conclude. So feel free to stop me and ask any questions whenever you think there is some confusion or you want to ask something, please feel free. Okay. So, okay. So let's start with algebraic complexity. So in algebraic complexity, in complexity theory, the main goal is to prove P not equal to NP using maths and using mathematical tools. And this is one of the most important question in theoretical computer science as well. So this is kind of an in the intersection of theoretical computer science and mathematics. And there have been some efforts to prove P not equal to NP, but most of the efforts have failed because in 1994, Rutich came up with this natural proofs barrier. They said that, well, essentially all the sort of natural proofs, I will not define what do you mean by natural proofs, but all these natural proofs cannot really separate P from NP. And so at that point, people really lacked what could be the potential way to separate P not equal to NP, because most of the methods known till that time actually was natural kind of in some sense. So there were some natural proofs, so they could never potentially prove P not equal to NP. Now to break that barrier, Mulmula and Sohoni published their paper GCT1, Geometric Complexity Theory 1, and they proposed sort of a program which we call now GCT program, Geometric Complexity Theory program, and they describe a method which is essentially can break that barrier. And I think towards the mid of the talk, I'll slightly go through the reason why it can break the barrier, just to give you the intuition and why GCT could be one interesting aspect to look into proving P not equal to NP. But anyway, so they came up with the GCT1, and this was built on Valiant's algebraic complexity theory framework, which is VP not equal to VNP. I'll define VP, VNP, and so on just in a few more slides. But for the time being, let's think of this as I have P not equal to NP conjecture, and there is some algebraic version of P not equal to NP, which is VP not equal to VNP, and Mulmula Sohoni sort of built this GCT program on VP not equal to VNP. In fact, they strengthened this. And to do that, they defined border complexity, which was in the same year independently defined by Burgi sir as well. Okay. And we will be working with this algebraic notion of order complexity that Burgi sir defined. And finally, in the subsequent paper, GCT2, they actually proposed representation theoretic formulations, and they said that we need to understand this representation theory to actually, and if we really understand those representation theoretic problems, we can actually prove such strong lower bounds. So this P not equal to NP problem was sort of completely translated into representation in this representation theoretic language, and there are some things that you want to prove. I'll not exactly point out what are the exact things you want to prove, because to do that I need to formally define a lot of things which I do not have such time. But let's just think of this as a mathematical program you want to prove P not equal to NP, and GCT is exactly does that using representation theory. And this is one of my favorite codes that I often use from Scott Aronson's P equal to NP, whether P equal to NP book, where he actually compares GCT with string theory. And essentially he says that like string theory, we really don't have the sort of foundation, mathematical foundation to understand GCT, but still we are impatiently trying to understand GCT like we are trying to do this in the string theory. But essentially we want to unify. String theory tries to unify results in physics, and GCT tries to unify complexity theoretic results or lower bounds in terms of algebraic geometry and representation theory. So these are sort of very similar in that flavor. So yeah, so hopefully towards the end of this talk, you will get some flavor of the string theory of computer science. Okay, so what's the model of interest? These are algebraic circuits. What's an algebraic circuit? It's like Boolean circuit, but instead of AND and OR gates, you have addition and multiplication. And in the bottom, you have some variables, some field constants like 1, 2, anything. And even, in fact, you can use these constants in the edge, on these edges. And they naturally compute a polynomial. For example, this is plus, this is 4. 4 means this is computing 4 times x1. This edge is computing x2. And there is a plus, so that means this is computing 4x1 plus x2. And similarly, the multiplication also computes naturally. So ultimately you will be computing some polynomial f. So what are the interesting measures? One is size of the circuit, which is the size of the graph. So you can think of this as a graph, acyclic graph, directed acyclic graph. And the size we'll be working on is number of nodes, i.e. number of vertices and number of edges. So there are different notions of size of the circuit. Some people consider some number of nodes. Some people just consider some number of edges, but they are polynomially related. So it's fine. As long as you were trying to prove some super polynomial lower bound or something, this size actually won't really matter. It's fine. So this is the size of the circuit, and size of the polynomial f is essentially the minimum size circuit computing the polynomial f. There could be many circuits computing the same polynomial f, and we want to compute the minimum size of all the circuits. That is the size of f, size of the polynomial. So this is one important measure. And the third is the depth. This is depth 3, because from the bottom to top, the depth is 3, right? And we will be talking about depth 3 circuits only to almost towards from the half towards the end. So this is sort of an important thing to remember. The depth, that is the longest path from bottom to top. Okay, so now once you have defined the computational model in complexity theory, what we really try to do is come up with easy problems and come up with hard problems. Means I have a model of computation. I want to understand what are the problems that are easy in that model. What are the objects that I can compute that is easy? That means we can efficiently compute in that model. And what are the hard polynomials? That means it requires some, large amount of source. And in this case, amount of source meaning size, let's say size of the circuit. because circuit is my model and measure is the size. So let's first look at easy polynomials, some easy polynomials. And we define VP variance P. This is sort of an algebraic analog of the class P. And this has a sequence of polynomials Fn such that both size and degree are bounded by polynomial in N. Okay, and you can ask why this degree bound is also required. Well, essentially there are other polynomials as well. For example, let's say x to the 2 to the n. This has order in size circuit. You can just multiply x to x squared, then x to the 4, then x to the 8, and so on. Like quadratically, you can improve. Compute the polynomial x to the 2 to the n in order in size, but we will not consider that in VP because the degree is exponential. So we will only be considering polynomials where the size, that means circuit size, and the degree, both are polynomially bounded. So this is my easy definition. So if a polynomial family Fn is inside VP, that means we sort of say that this Fn is easy. So let's see some example. These are my 3 examples. For example, just a monomial x1 up to xn. This is a trivial circuit, right? You just multiply x1 up to xn. There is this product get, and you have this x1 up to xn variables at the top, and that's it. Similarly, you can compute x1 to the n plus xn to the n, this polynomial as well easily. So this is also in VP. And a rather more interesting polynomial is this product 1 plus xi polynomial. So when you look at this as product 1 plus xi, this is a trivial small size circuit because you take 1, you take x1, x2, xn, there is a product get. So if first you plus add it to get 1 plus x1, 1 plus x2, 1 plus xn, and you just multiply. So this is a very small size circuit. However, if you expand this is like exponential, like 2 to the n many monomials. So when you think of this as sum of product, it may not be obvious to see it has a small size circuit. So there could be many monomials, but there is a syntactic way to represent this polynomial as a small circuit. So what really a circuit does is it's sort of a syntactic representation of a polynomial where ultimately there could be many monomials, but it sort of shows that it can be easily computed. And another way of thinking this VP is the circuit size is really capturing how many additions and multiplications are required to compute that polynomial. And when we say that this is in VP, we are really saying that the number of additions and multiplications, that means number of operations to compute that polynomial f is really small. Small meaning polynomially bounded. So this is my VP. And the other easy polynomial that we'll be working with is the determinant polynomial. We have all seen the determinant polynomial from our 11th or 12th class. We know how to expand this, but mathematically speaking, this is like just the sign of the permutation, and you take you sum over all the permutations. This is essentially this plus minus that happens. So what is the determinant polynomial? You take a symbolic matrix n cross n, and each entry is xij, new variable xij. And if you just like the way determinant is expanded, you just expand this. There will be just plus minus, and this will be just xi pi I kind of thing. This will be a monomial, and it's like an exponential sum of monomials plus minus. And this is the definition of determinant, symbolic determinant. And the point is why I'm talking about this is determinant is universal, and by universal I mean that any polynomial f can be actually written as a projection of determinant. And by projection I mean that you take a determinant. So suppose I am given a polynomial f. So I claim that there are linear polynomials, a linear meaning degree less than equal to 1, such that and there is some determinant n cross n. It in may depend and mean can be exponential as well, but there is some determinant such that each entry you put linear polynomials, right? And determinant of that matrix will exactly be this f. So that's why we call this determinant as universal. So this property is not really, it's not very trivial to prove, but you can prove that. Okay. And now the point is that since any polynomial f can be written as a determinant, there could be many determinants, right, to computing the same f. So you talk about the minimum dimension of the matrix. So that we call as determinantal complexity. So remember we talked about size, which is the size of the circuit. And the second measure we were talking about is determinantal complexity. And I'll give you an example. For example, look at this example x1 of x and a monomial. I claim that this is determinant of x1 of x and this diagonal matrix with just xi is in the diagonals and all other things are zeros, right? So of course, from this example, it is clear that determinant complexity of x1 of xn is at most n. Now this is exactly n because if it is n minus 1 cross n minus 1, it cannot even compute an n degree polynomial. See, x1 of xn has degree n. And if the dimension is n minus 1 cross n minus 1, since the entries are linear, it can never compute an n degree polynomial. So it has to be exactly n. So this is also an a measure that we can talk about, which is determinant complexity. Now, with this determinant or determinant complexity, we can again define another class, which we call VBP. BP is for branching program. So in the Boolean complexity also there is this notion of branching program, but this is algebraic branching program or variance branching program. So this is essentially all the set of polynomials where they can be, I mean, their determinant complexity is bounded. So when this was VP, it was size. When this is VVP, it is determinant complexity. Okay. And you can show that determinant has a small size circuit. Symbolic determinant has a small size circuit. So that means this VVP is actually inside VP. And is actually open to prove whether VVP equal to VP or not. Okay. But yeah, so why so that's why I have written this easy class, because as we said, VP is easy, VVP is also easy in some sense, because you can, I mean, of course, one definition is that it has small size circuits, but in fact, yeah, it has also small size determinantal complexity as well. So these are my easy classes, and they have numerous connections in linear algebra, volume, and so on, because determinant naturally comes up in this planar matchings and so on. So that's why this VVP and VP and these polynomials come in other connections as well. Okay, so now once we have defined easy polynomials or seen some easy polynomials, let's just ask, what do you really mean by hard polynomials? Now already I said that in complexity theory, by hard we really mean that the amount of resource is a lot. And in terms of algebraic circuit complexity, what we really mean is that the size of Fn, the circuit complexity of Fn, is super polynomial in N. Okay, so this is not actually in VP, let's say. This is, so these are the kind of hard polynomials we're looking. So the question is, are there hard polynomials? I mean, does there exist a Fn such that it requires super polynomial size circuits, or is it the case that every polynomial has polynomial size circuit, right? And now it is known that a random polynomial, even if you restrict your coefficients to 0, 1, that is also hard. Okay. So that means there are plenty of polynomials which are hard. But of course, the question is find an explicit one. And by explicit one, I mean that we want to compute the coefficients of this polynomial. So in this polynomial, there could be many monomials, and I want to understand how easily computable the coefficients are. If they are easily computable, then we say that this is explicit. A random polynomial is not explicit because it's not, I mean, even if it is 0, 1, it's not explicit because you cannot compute when it will be 0 or when it will be 1. It's like a random thing. And we want to remove the randomness.
So is it like, for every monomial with a random, with a probability you have 1 and with a probability 0, you...
Right. Yes. You can think like that. Yeah. So, so the target is now to find an explicit polynomial where I know how to compute the monomial. So given a monomial, I will know what is the coefficient of that. Okay. Now,
question?
Sorry?
So this random polynomial, can it be a multilinear polynomial even?
Yeah. In fact, this hard polynomial they proved that was actually a multilinear polynomial. So the proof actually they talked about. I mean the proof, if you look at, they actually show that the random multilinear 0-1 polynomials are hard. In fact, I mean
So these are F2 polynomials, like.
No. So the field actually is let's say over complex or rationals. I mean, you can do anything, but I'm saying that you can even restrict the coefficients just 0-1. So it's not like you are working over F2. So why this is important is because we always talk about determinant, permanent, and these things, right? So they have like bounded coefficients, right? Or like 0-1 or +-1 coefficients. So one could also ask, right? I mean, maybe if you restrict your coefficients, the hardness may change. So this paper really shows that it does not matter what your coefficient is. You don't really have to use large coefficients and so on. Even like 0 or 1 coefficient or +-1 coefficients are enough to show that even random polynomials are hard.
So over F2, does it fail, or we are still open?
No. For if over so actually the point is that again, the point is that if you talk about random, then it is because the point is that you know that given any boolean, I mean, in a random function requires large circuit, right? Large boolean circuit, right? So you can always multilinearize and so on, and that is my F2 polynomial. So that corresponding polynomial will also be hard.
Okay.
But that is not explicit. So yeah, so over F2 also this is known that nothing is, that also proof works over F2, but I'm saying that over F2 my only choice is 0-1, but even over rationals, even over complex, I can restrict myself to 0-1. Remember why the difference I'm saying, okay, I think this is the point I should make. Remember, my circuit can use any coefficients. So that is where the underlying field may differ. When you are also working over F2, even the circuit, you are allowed to only use 0 or 1. There is nothing else. Now over, let's say, rationals, the circuit may be using some random coefficients, some random values, some random field constants. But ultimately the polynomial that you are computing has just coefficients 1, let's say. I mean, 0 means this is not even there, but yeah, or just 0-1 coefficients. Is the difference sort of clear what I'm trying to say?
Yeah. Very nice.
Yeah.
So here counting arguments will not be enough, is it?
So over finite field counting argument is fine, but over Q as like characteristic infinite file, but essentially you can quantify this using algebraic geometry and say that okay, the variety, you take a variety and this deep dimension is this, and then they cannot intersect, I mean, and so on and so forth. So the Bezier kind of bound you use, and then but essentially the flavor is same. Yeah. So that again, so the target is explicit, to find an explicit polynomial which is hard, which requires super polynomial size circuit, and the one of the
maybe sorry Pranjal, maybe a couple here sometimes using non-trivial coefficients or constants, not coefficient, constants can bring down the complexity of the polynomial, right?
Right. That is why I'm saying, that is why this 0, I mean, that is why I'm saying that, I mean, this is more important, this statement is more important, because what we are really saying that, I mean, you can work over rationals or complex or whatever, and you can use arbitrary constants in the circuit.
Right.
That is the difference over working over F2 that someone asked me that, okay, I mean, what about F2? But in F2, we don't have the choice of using such constants. But this statement is true even over complex. So in the circuit, when you are working over complex field, you are allowed to use any arbitrary constant in the circuit. So that actually could have brought down the complexity, right? I mean, who knows? I mean, you could be using some random constants, and then the circuit complexity should be, I mean, the circuit complexity may be easy, but this is showing you no. I mean, you use whatever complex constants you want to use, and I know that target polynomial is also easy. I mean, easy meaning the coefficients are just 0 or 1, but still this is hard. There is no small circuit for that, and also multilinear. So those things are also there. So does that answer your question or this?
Yeah, I was just yeah, Pranjal, carry on.
Yeah. So now the point is that this is permanent. So the one of the candidate polynomials is permanent, and permanent has this just all plus one, all coefficients one. So think of this permanent as also like this polynomial. Forget about random, but this is like a 0, 1 coefficient, right? There are some monomials there with coefficient 1, and there are some monomials which are not there, which is like essentially 0. And we want to really show that this is hard. And why this is explicit? Because given a monomial, I can understand whether the coefficient is, I mean, what is the coefficient of this, whether this is 1 or 0 for the permanent. Okay. So then the question is that can I, so this is the explicit point, this is an explicit polynomial. The question is, can I show that this is hard? I mean, this is, but I'll come to that. But before that, the similar flavor that I already talked about determinant, we can show that permanent is also universal. That means you take any polynomial f. I claim that there is a matrix such that if you look at each entries as linear polynomials, then permanent of that matrix xn will be the actual polynomial f. So in the previous slide it was determinant. In the current slide this is permanent. So I'm saying that like determinant, permanent is also universal. Any polynomial f can be written as permanent of some matrix where each entries are linear polynomials. And again, since any polynomial f can be written in such a way, there could be multiple representations. So you take the minimum dimension, we call it permanental complexity or PCF. So till now I have defined 3 measures: size of f, which is the circuit size; determinant complexity of f, which is DC of f; and permanental complexity of f, which is PC of f. Now, once we have defined this permanental complexity, using permanental complexity, we can also define the another class which is called variance NP. Okay. So the definition is this has all the sequence of polynomials such that permanental complexity is polynomially bounded. So till now I have defined 3 classes: VP, VBP, VNP. Okay. VP was size of Fn is polynomially bounded and degree as well. VBP was determinant complexity. VNP is permanental complexity. So think of this as one. Whenever you have a measure defined, you can correspondingly define a circuit class. And this permanent actually comes in again many complexity theory proofs. For example, this is closely related to Sharpe class. So essentially enumeration, counting, matchings, and those things naturally pop up in, I mean, this actually, I mean, you will see VNP polynomials in many cases. But yeah, so what is known? As I said, I defined 3 classes: VVP, VP, VNP. It is known that VVP is inside VP, is inside VNP. Okay. And the conjecture, the famous conjecture is that these classes are separated: VP not equal to VNP and VVP not equal to VNP. So in terms of determinant complexity and size, VVP not equal to VNP really means that permanent does not have small determinant complexity, and VP not equal to VNP means permanent does not have small circuit size. So they both should be polynomially, super polynomially large. In fact, we expect this to be exponentially large, but even super polynomially large suffices. This is the sort of algebraic version of P not equal to NP. So any questions till now?
Good.
Okay. So now I'll quickly go through some connection. So the first question is, I mean, why are we even interested in proving VP not equal to VNP? Does that achieve anything? I mean, except of course mathematical interesting problems and so on. What is happening in terms of complexity theory? Let's say theoretical computer science. So now it is known that P the non-uniform version of P not equal to NP, which is the circuit version, which is P/poly not equal to NP/poly, actually implies these separations over finite fields. And in fact, if you assume GRH, if you assume a Riemann hypothesis, then this also holds over Q or over complex as well. So essentially, this is saying that if we really believe P/poly not equal to NP/poly or non-uniform P not equal to NP, then the algebraic P not equal to NP, that is VP not equal to VNP or VP not equal to VNP, they must be true. So in some sense, this is implying that this may be easier to prove than proving this. I mean, of course, this is the correct direct implication. I mean, this will definitely prove this. So, but now the point is many people try to make is that, look, I mean, if we really want to understand P not equal to P are separate, we really have to go via this line, and there is no other way. So we really need to prove this before understanding P/poly not equal to NP/poly or P not equal to NP. Okay. So this is the kind of message that this paper tried to convey. So yeah, so this is one interesting connection that I wanted to make sure. And also, we just to make sure, so we do not really expect P/poly not equal to NP/poly. Otherwise, actually, this pH collapses and so on. So there are multiple results that is known. So we really expect that these are separated. So yeah, so that is one interesting point which I wanted to just convey before moving forward. So yeah, so let's just summarize this section and then quickly move on to GCT. So a recent breakthrough result came in last year where actually super polynomial size lower bounds were shown for constant depth algebraic circuit. It was not known a priori. So they sort of showed that there is a class of polynomials where it requires actually constant depth. I mean, so if you want to write this as a constant depth circuit, if you want to compute this as a constant depth algebraic circuit, it has to have super polynomial size. And there are also this, if you remember, I talked about these natural proofs. So there are actually questions whether VP not equal to VP, you can to prove that whether algebraic natural proofs can exist or not, and there are some partial answers known, but this is also another interesting paradigm which I will not be talking about, but this is also another interesting, yeah. And then this proves actually they have intimate connection with lower bounds like as well. Okay, so once I have summarized this, let's just go and leave these things in the border. And what do you mean by border and so on? So the question is can approximations help in computational models? And so there are a lot of questions that you can ask, that what do you mean by approximations, and to start with, right? So to do that, I just want to quickly go through one interesting measure, because I think this is the simplest measure to understand and convey why border complexity is interesting to look at. So the measure is called Waring rank. Let me define what is Waring rank. So Waring rank of a polynomial. So we'll be talking about homogeneous polynomials just to clear it out. So what is a homogeneous polynomial? Each degree monomial. So it's a polynomial where each monomial has degrees same degree. Okay. And what is a linear form? When this is a homogeneous linear polynomial of the form a1x1 plus an(xn). Okay. So what is now the Waring rank? You want to write this homogeneous polynomial h as sum of powers of linear forms, li to the d. Now the r, this minimum r that you can write such h is called the Waring rank of h. Okay. So the point is that again, any polynomial can be written as sum of powers because any monomial can be written as sum of powers. It might be large. Actually, for monomials, it is known that this r should be large. But I'm saying that for any monomial, you can write this as sum of powers, linear powers. So then any monomial can also be written as, because you just write each monomial as sum of powers and then just add it up. So that means Waring rank is finite. And I think I will be eventually using this notion, which is called depth diagonal circuits, which is again sort of sigma with sigma. This is the definition depth 3 circuits. But yeah, for the time being, you can forget this notion if you want to. Just focus on this Waring rank. So again, just to reiterate what is Waring rank, I want to write H as sum of powers of linear forms. The minimum R such that I can write H as that is called the Waring rank, and Waring rank is finite. Okay. So let me give some example, and to do that, and I'll give some example, and I'll see why we needed to adopt this border notion. Okay. To do that, I'll be probably talking about the simplest sort of setting that is possible. That is, let's just talk about bivariate degree 2 polynomials. So there are two variables x and y, and let's say it has degree 2, and I want to understand what are these polynomials h such that its Waring rank is 1. Let's just try to characterize, or let's just try to understand when h, there's a bivariate polynomial, when can h be Waring rank h is 1. Okay, so since this is a bivariate degree 2 polynomial, this is ax square plus bxy plus cy square. Now I claim that all the polynomials h such that Waring rank is 1 is eventually all the tuples a, b, c such that b square minus 4ac is 0. You can actually show that. You can actually show that. So Waring rank 1 meaning this has to be something square, and you can show that that means they satisfy this thing. And if some polynomial satisfies this ABC, then any polynomial h can be written as a single square. That means Waring rank 1. Okay, so now you may ask that what is why are we even talking about this x1? Now I claim that if I understand this x1, this characterization, this coefficient characterization, I can use it to prove a lower bound. For example, I claim that Waring rank of xy is greater than 1. You can show that xy can never be written as single square. It's just sort of very trivial to show that. You can just write it down and see that xy can never be written as a single square. It requires 2 squares. But I'm saying that another way to prove this is to look at this x1. I know if it was actually 1, I know that 0, 1, 0 will be in this set x1 because I have characterized Waring rank equal to 1, right? I know that if it had Waring rank 1, b square minus 4ac has to be 0, but this xy is what? 0 times x square, 1 times xy, 0 times y square. So 0, 1, 0. So I'm saying that 0, 1, 0 is not in x1 because 1 square minus 4 times 0 is non-zero. So it cannot be in x1. So this is another way to prove lower bound. If I can characterize this set, and by set I mean that the coefficients, if there is some such kind of equation, I can actually prove a lower bound. So we call this polynomial b square minus 4ac as a separating polynomial or a polynomial obstruction, and I'll tell you why this is a separating polynomial, because this actually separates, but that will be clear in the next slide as well. But for the time being, let's think of this as a separating polynomial. And what is the property of x1? So I claim that x1 is a closed set, and by closed, it really means that if I have a sequence of points where limits exist, let's say an goes to a, bn goes to b, cn goes to c, then all the limits points are also in the set x1. Then it is like it is closed. Otherwise, it is not closed. If there is some limit which is outside x1, some set, we call this, we will not call this closed. We will call this open. But in this case, this is closed because the limit points also exist in the same class. Because you can just take a and b and cn. I know bn square minus 4a and cn is 0, and bn square goes to b square, an goes to a, cn goes to c. So b square minus 4ac is also 0 automatically. So x1 is actually a closed set. Now, why x1 is closed set is important, that we'll just see in this slide. So I claim in this slide that approximation really helps. To do that, let's go to this example, x square y. I claim that Waring rank of x square y is 3. Why? Because there are these 3 cubes 1 by 6 times x plus y cube, 1 by 6 minus. So 1 by 6 you can take inside, cube root of 6 and take it inside, that's fine. Because let's say we are working over complex and so on. So 1 by 6 times x plus y cube, 1 minus 6 by times 6 minus y cube, 1 by 3 y cube. This is an expression you can just verify. That means x square y can be written as sum of 3 cubes. That means Wadding rank of x square y is less than or equal to 3. Okay. And in fact, you can show that it is exactly 3. There is no way you can write this as the sum of 2 cubes. You can show that. Okay. So we know that Wadding rank of x square y is 3. Now let's look at some interesting polynomial. So think of epsilon as non-zero parameter. So I am not allowed to put epsilon equal to 0. Okay. I am allowed to put anything but 0. Look at this polynomial. So think of this some parameter. Let's say think of this as some parameter epsilon, and let's say I have this polynomial x plus 1 epsilon y cube minus x cube and 1 by 3 epsilon. And I claim that when epsilon tends to 0, you actually get the x square y polynomial. You can just expand it out and take epsilon tends to 0. Then this guy vanishes. This guy vanishes. Just x square y remains. So what is happening here? What really is happening is that there is this h epsilon polynomials. They have Wadding rank less than or equal to 2. So think of epsilon as some real number, right? So then this is like sum of 2 cubes. So this has Wadding rank 2 for non-zero epsilon. As I said, you cannot really put epsilon equal to 0. And h epsilon tends to h. The limit is x square y, but the moment you reach x square y, its Wadding rank cannot be 2, it is 3. So this is another a good picture which will actually describe what I'm trying to say. So let's think of this all polynomials where Wadding rank less than or equal to 1. Then this is polynomials where Wadding rank less than or equal to 2, Wadding rank less than or equal to 3, Wadding rank less than or equal to 4. I am claiming x square y sits in the border. Okay, why? Because I have some polynomials h epsilon which are all inside this, and taking limit. The moment you reach the limit point, it cannot be really inside. So it sits in the boundary. Okay, so this is exactly why this border notion came. So now I'll actually generalize and say how to define this border complexity.
Hey, Pranjal. So how do you show that Wadding rank of x square y is at least 3?
Oh, you just brute force. Actually, you can just show a brute force by showing that. Okay, let's say that x square y is.
Do you have an discriminant for that as well, or?
Sorry, do you have
a discriminant for that as well in some sense?
Yes. For cubic, you can go to discriminant and so on and so forth, but for higher you cannot. But yeah, that is also that. For that, if you remember this x1 set, that is also known. This set of H such that Wadding rank is let's say so cubic polynomials such that you want to understand Wadding rank 3 or 4 or 5. I mean, I think for till 4 it is known, but yeah, that set is known actually. Above that, it is not known. But I'm saying that you don't really go into that set definition. I mean that x1, the characterization. You can just by brute force say that okay. I mean, let's assume that this is sum of. Let's assume that this is sum of 2 cubes, and you can show that this is never possible.
Oh, makes sense.
Just
yeah, makes sense. Thanks.
So now once you have defined, so this is something peculiar that is happening that I already said. So once we have defined this, let's just define border Wadding rank, and yeah, I'll define that. But okay. So there is a catch that I wanted to mention. The first point, there is a subtlety, and the subtlety is that if you remember this b square minus 4ac polynomial, so if there is a continuous function, let's look at this. Let's look at x1, or let's look at x1. If there is a continuous, this is a continuous function. If there is a continuous function that vanishes, that is exactly 0. Then it must be a closed set. That means that it will also, in the limit also, the points will also vanish. A and B and C, and then the limit points A, B, C will also vanish. So automatically that will be a closed set. So this cannot be used. So a continuous function like if cannot be used to prove a lower bound. Let me get into this. Again, let me rephrase this, reiterate this point. I'm saying that if f was really a continuous function, for example, f can be thought as b square minus 4ac, and if it vanishes on varying rank less than or equal to 2, then it should also vanish on x square y, because x square y is in the limit, as you show. But as I told you that x square y cannot have varying rank 2. That means to separate these lower bounds in terms of these sets or these separating polynomials, we really have to come up with a discontinuous function that vanishes on all the varying rank less than or equal to 2, but cannot vanish on x square y. And this discontinuity is what we really want to avoid. I mean, in mathematics, we really want to talk about continuous mathematics and so on, so that the life is easy. In fact, polynomials in particular, if it is possible. So for that, we define border varying rank. So what is the border varying rank? So the border varying rank is, I am saying that when h can be approximated by polynomials of varying rank less than or equal to n. For example, x square y has border varying rank 2, because if you remember, I defined this h epsilon polynomials. H epsilon polynomials has border rank h epsilon has varying rank 2, and h epsilon approximates h, because h epsilon tends to h when epsilon tends to 0. So then we say that border varying rank of x square is also 2, but varying rank is 3. Okay. And as I said, now the subtlety is gone, because if we talk about these approximations and so on, then actually we can show that this is a closed set. And by closed set, I really mean that to show this lower bound, you really have to find a continuous function. So this continuity is gone now. So the message I'm trying to convey is that for showing varying rank lower bound might be harder, although it is not known. But I'm just saying that it might be harder than showing border varying rank in terms of mathematics. Why? Because what we are really showing is the characterization of this set xn, the sets h, such that border varying rank less than or equal to n. This is a good characterization. This is a good set in some sense, rather than if we remove the border. So we really want to, if we want to show a lower bound for border, then border varying rank, then we really have to find a continuous function f that vanishes on this, but does not vanish on this particular polynomial p. That's it. That's what I wanted to show. I mean, convey. So once I have defined border varying rank, I just quickly want to go to border complexity definition. So you can replace border varying rank by any gamma, any measure gamma, and we say that for a measure gamma, what is the gamma bar? All this h epsilon, such that h epsilon has limit h, and the gamma of h epsilon is less than or equal to n. Then we say that gamma bar of h is less than or equal to n. Okay, so you define, so in this side there is gamma, in this side there is gamma bar, and there is this limit. So if h epsilon has limit h, and gamma of h epsilon is less than or equal to n, so we will say that gamma bar of h is less than or equal to n. And this is also important in matrix multiplication and so on. I want to quickly end and then go to border complexity. But yeah, so this is what I wanted to say. I hope that this, at least some parts of it is clear, because this varying rank and border varying rank definition, actually this difference is what sort of started this border notion, because border varying rank and so on were all defined lot earlier. This was known in mathematics, but yes, and we want to really now take these components and try to use this in complexity theory, or formalize the questions. So, but you can ask that, okay, fine, these definitions are fine. I mean, this is some mathematics that is going on, but I mean, what is really happening in terms of computation? Can we really say something about computation? Because this is really in some sense abstract. So to do that, we will define approximative circuits, and this is, I think, this is the definition that we will be talking about. Approximative circuits, which is actually, I think, in my opinion, is easier to understand. But this definition are all equivalent. I mean, working over this definition and working over this border complexity that we already defined in terms of size and determinant complexity and so on are all equivalent. But let's just focus on approximative circuits on this. So if you remember my definition of circuits when in the first slide, what I said is I have some, it's a circuit I have some variables, some constants. In between, I can use some constants from the field, and it computes a polynomial. So now, instead of this field f, let's think of this field as f of epsilon. Epsilon, think of this as some variable for the time being. Okay. And f of epsilon means the rational field. That means I am allowed to use all these kind of functions, 1 by epsilon cube, epsilon by epsilon cube plus 1, all this, and there is no cost. So think of epsilon as free. You can use anything you want on the edge. Okay, or here 1. I mean, instead of 1, you can just use 1 by epsilon cube, something like that. Now this is a polynomial. You are computing a polynomial over this field f epsilon, and the variables are again x1 up to xn. So this is a polynomial, right? This is a polynomial over this field f of epsilon, and you want to understand what is the limit of this polynomial. That means what happens when epsilon tends to 0. What happens to this g? Okay, so let's try to understand that. So I'll assume that, just a small catch here, actually the epsilon powers can be negative as well, right? As we are using 1 by epsilon cube and so on. But for our purpose, let's just assume that it is, in fact, ultimately it is being cancelled and so on, and ultimately it is a polynomial in epsilon as well. So not only it is polynomial in x1 up to xn, it is also a polynomial in epsilon. So there could be 1 by epsilon in the circuit, but they somehow gets cancelled. Is there any question?
Hi Pranjal, there's just a comment. Yeah. The output should be in fx comma epsilon, right? Not.
Sorry. Yeah. So here, that is what I'm saying. I mean, but yeah, right. You are right. It should be fx comma epsilon, right? So, but from this picture, I mean, what I wanted to say is, essentially this is computing a polynomial in epsilon x. Right. But yeah, ultimately for the definition to work on, you are right that I want to work with this. This as we pointed out, fx1 xn and epsilon. So yeah, so I have some g. So as Nitin said, that I have some polynomial g as computed by the circuit, and also assume that it is a polynomial in epsilon as well. That means it is a polynomial in x1 up to xn and also in epsilon. But I just wanted to make sure that in the circuit you are allowed to use 1 by epsilon, 1 by epsilon square, and so on. Okay. But suppose you are computing this polynomial g. Okay, and I want to understand what is the complexity of G0. By complexity, I mean that what is the circuit size of G0? Remember, G0 is the epsilon to the 0 coefficient. Okay, so what am I given? I am given this circuit where I am arbitrarily using 1 by epsilon cube, anything in between, and I want to understand what is the epsilon to the 0 coefficient of this polynomial that is being computed. Now you can say, I mean, come on, I mean, you can just put epsilon equal to 0, right? I mean, what is the problem on setting epsilon equal to 0? And the problem is that although epsilon equal to 0 is defined, that means G0 is defined, but you cannot really use epsilon equal to 0 in the circuit. So if you look at that circuit, you cannot put epsilon equal to 0. What does 1 by 0 cube mean? It is ill-defined. So you cannot really output that says, I mean, I am just putting epsilon equal to 0. That is exactly where the catch lies, that I cannot make epsilon equal to 0, but still I want to understand epsilon to the 0 coefficient. How hard is that? And as you can probably have understood already, that this is hard in some sense to understand. I mean, this might be non-trivial actually. How non-trivial? That is exactly what border complexity of GCT does. So let me define this then formally. So I say that if you remember, I have a G polynomial of size S. I have a circuit, right? I have a circuit given where I am using 1 by epsilon and so on and so forth arbitrarily from this field. And I want to compute the G0, which is H in this case. Epsilon tends to 0. And we say that if G has size S over F epsilon, then this limit polynomial H has approximative complexity S. So in some sense, H is approximated by the circuit's G of size S. That's why this approximative complexity. So again, I have a circuit G of computing G, but where I am arbitrarily using epsilon, there is no cost whatsoever. And I want to understand the epsilon to the 0 coefficient of G, which is my H. So if G has size S over F epsilon, that means you can use epsilon arbitrarily and there is no cost. then I say that H has approximative complexity S. Okay. Now, of course, size, and then we actually call this as size bar. Approximative complexity S of H means size bar of S, okay, or approximative size of S. So it is easy to show that size bar of H is less than or equal to size of H, because you can just take G as H. H of X is H of X plus epsilon times 0. So trivially, if you can exactly compute, you can obviously approximate. So this is the sense of this inequality. Now, if you remember, I said that you can assume that we assume that G is a polynomial in X and epsilon. Now, what could happen is that even if we are working over S, with size S, the epsilon degree can be exponential. It can be like 2 to the S square or something. So that is exactly, I will not get into that, but that is exactly why we cannot really interpolate and say that I put some epsilon values and I want to get something that will just give me exponential bounds. So what I'm trying to say here is that this approximation or approximative circuits and so on, and so exact complexity and border complexity may not be related. We do not really know, how to exactly relate this for the general circuits. So currently this is exponentially apart. And as I said, the idea is, since this is exponential, you can just randomly interpolate by putting different values of epsilon and interpolate to get G0, but that will give exponential blow up. So it is not, so this is the current known gap. We really, okay, yeah. So this is the current known gap. And we really want to understand what we call deborder. Okay. And what do you mean by deborder? Suppose I have a class C, I want to understand what does C bar mean. As we saw in the previous slide, there can be exponential gap, but the question is, can we say something when the class is nice? When we are not really talking about just circuits, just general circuits, maybe some restrictions on the circuits and so on and so forth. So the debordering questions, yeah.
So in the previous slide, when you said there is an exponential gap, so what is this? Is like if you have a lower bound on border complexity, then you have a lower bound on normal circuit. Whereas if you have a bound on normal circuit, now the bound on border you're getting is log of size.
Exactly, which in most of the cases it's trivial in some sense.
Yeah, but in most of the cases it's trivial. So the thing is, you want to improve this.
Improve. So in particular, if we can say that this is poly, let's say, then our life is great, because then essentially we are saying that a lower bound in proving in border and
if it is polynomially related, then you're trying to say going to border does not make sense.
It does not make sense. Or what we have to really talk about is all these mathematics or all these continuous functions or all these varieties and closed and so on, because essentially they're polynomial related. So what we are really saying is to capture that. So essentially they are being captured. One way or the other. You can think of in the both ways. Either border does not help or only border helps. That means that all these closed sets and so on make sense. So essentially to work with that, because that is mathematically more enriching, and that is easier to work with. There is no discrimination system. Why? Yeah. So it's like that. You can think from two perspectives. Yeah.
Makes sense.
Now, yeah, but now it is exponentially for the in general classes. So as I said, so since this is exponentially gapped, we want to understand what happens for a specific class C. Can we deborder in the sense that, okay, I may not know what is the connection between C and C bar exactly, but I want to come up with a D, another nice class, such that C bar is completely contained in D. There is no border here. Here is a border. So that's what we call this deborder. So in some sense, we are really saying that I want to understand C bar, and I am not restricting myself to only understand in terms of C. Here, remember, this is in terms of same circuits and so on. This, let's say, talk about general circuit. This is also general circuits, but let's not talk about that. We can also think of a slightly bigger class, but as long as this is a nice class, this is fine. So the debordering question is, given a C, which is some class C, I want to understand whether there is some D, such as C bar is inside D. Okay. So let's now come back to exact what I mean by that. Now you replace can see, you can replace this C by VVP, VP. This is border, this is Waring rank, VNP, anything, any class you want. Okay. Now these questions are all open, whether VVP bar is VVP, VP bar is VP, VNP bar is VNP, and so on. Okay. All these questions are open. And I just want to quickly point out this, and then I have, I think, 2-3 slides left. So I'll take maybe 5-6 minutes more. So so recall Valiant's conjecture. What was Valiant's conjecture? Valiant conjecture that VNP not equal to VVP or VNP not equal to VP. That means determinant complexity or circuit size should be superpolynomial. Now you can strengthen that, and you can say that, okay, not only just VNP not inside VVP, I want to prove that VNP not even inside VVP bar. Similarly, VNP not inside VP, just not VNP inside, not inside VP. I want to in fact prove that VNP is not even inside VP bar. Note that VP is inside VP bar, VVP is inside VPB bar. So this is a stronger separation that we are trying to prove. But in terms of this complexity classes, complexity measures, I am talking about determinant complexity bar, size bar. And this bar, if you remember, I said that given a gamma, you can define gamma bar trivially, like you have H epsilon, gamma H epsilon less than equal to n, and H epsilon tends to H, then gamma bar of H is less than equal to n, right? From any gamma, you can define gamma bar. So from determinant complexity and size, you can define these bar classes. So even with these complexity measures, you want to show superpolynomial lower bounds. These are the strengthening. These are sort of, as I said, strengthening, because this is a stronger separation, because just proving VNP not inside VP does not imply that, but VNP inside, not inside VP bar does imply that VNP is not inside VP, because VP bar is a larger class. Yeah. I'll not get into that, I thought, but yeah, okay, just maybe just one point. The another most important point, I think, which is why GCT was founded and so on and so forth, is that this determinant permanent, both polynomials, that they have nice symmetries, and by symmetry I really mean that representation theoretic symmetries and so on. I will not get into that, but they can be uniquely, in some sense, up to constant, uniquely determined. I mean, by these symmetries. So there is a set of symmetries which will define uniquely determine determinant or define determinant. There is a set of symmetries which will uniquely determine or define permanent. And now this property symmetry is something nice, because very few functions have nice symmetries. So remember the proof barrier I was talking about in the first slide, that P not equal to NP has this barrier, that most of the proofs we know are sort of natural proofs, and natural proofs cannot really prove P not equal to NP. That was the result of Razvarov-Rudich. And the point was, and when do we call a proof natural proof? One of the criterion was most of the functions. So if we want to separate, so think, it's a bit philosophical, but think of, if I want to separate P not equal to NP, what should be a way? I want to come up with a function such that, or a property such that P has a property and NP does not have a property, or vice versa. P does not have that property, but NP has a property, right? But this paper actually showed that all these natural properties, and by natural means that, let's say that property, many polynomials have that property. That property cannot use that property cannot be used to prove P not equal to NP. But here the interesting point is that determinant and permanent has nice symmetries, and very few functions can be symmetry characterized. That means very few functions have this property symmetry characterization. So given us some properties, we want to uniquely determine whether this is determinant or permanent, and they have nice symmetries. Few functions can be uniquely determined by the symmetry. So the symmetry is not really a natural property. So that means it sort of avoids this barrier. So that means this can actually be used as a proof. But now you can ask that, okay, I mean, now we are really talking about algebraic circuits, right? Where is this P not equal to be coming? But I'll not get into that. But actually, you can also come up with some polynomials, it is not determinant or permanent, some polynomials, they will also have symmetries, and you can show that if you separate them, you can show some lower bounds, then that will imply P not equal to NP. Okay, I'll not get into that, but the point was it's in some sense avoids this barrier. So we still have hope. If that is why actually this DCT and so on, people were very interested, because it naturally looks into the symmetry properties and that does avoid this barrier. Okay. So now I'll not get into this. Let's not. So how much time do I have? Do I have 5 more minutes? Because I think I have 2 more slides, but I may take 5 to 10 minutes. But if I don't have, then I'll just go to the.
So we have time for until like. So let's go for 10 minutes and then we'll have discussions for. Like,
right. Yeah, 10 minutes is fine, because I think I have.
So what is it? Girish and Arvind, like.
Yeah, I'm fine with 10-15 minutes. Yeah.
Arvind.
Okay.
Arvind, okay, let's.
Okay. So let's just so I'll skip this. What are the known results and so on so forth, and why debordering and so on so forth. Let's just come to depth 3 circuits, because I just want to. Okay, so now I'll come to our result and what does it say and so on. So let's just to understand that what are depth 3 circuits. So we will be talking about depth 3 Fanin K circuits. What do they compute? They compute sigma K pi d sigma. So they compute of polynomials of the form sum of product of linear polynomials. Okay, linear polynomials are just a0 plus a1 x1 and xn. You are taking products and you are summing up k many things. That is the sigma k, this k, product Fanin is d, and sigma is this linear polynomials that is being computed. Now the first question is that how powerful are they? Are they universal for constant k? We will be talking about constant k. Are they universal? And the point is that there are polynomials. This is the inner product polynomial x dot y on k 2k plus 1 variables. So you take x1 y1 plus xk plus 1 yk plus 1. This is simple polynomial. I claim that you cannot write the sigma top-fanin k circuit cannot compute this polynomial, no matter how your product Fanin large is. I mean, you can assume your d to be exponential as well. You take exponential in k, doubly exponential in k, whatever. You can take your d to be arbitrarily large. I'm saying that no matter how your large d is, you can never write this polynomial as sigma pi sigma with top-fanin k. But note that it has obviously trivial top-fanin k plus 1 pi d sigma. Sigma, it is obviously in sigma k plus 1 pi 2 sigma, but it can never be computed as sigma k pi d sigma. Why am I saying this? Because I just want to tell you how weird or how powerful can the border classes be. So the same questions can be asked in the border class, right? So I have a sigma pi sigma. I have a border, and just to reiterate what is the definition of border. So I say that H is in the border of depth 3 Fanin K if there is a G such that G is H plus epsilon times something. So epsilon to the 0 coefficient is H, and not only that, G is computed by this sigma pi sigma circuit over this field F epsilon. If you remember that you can arbitrarily use 1 by epsilon and epsilon in the inside the circuits as a constant, and the limit is H. And this has size S over F epsilon. There is no epsilon. I mean, epsilon has no cost as usual. So the question is how powerful these border circuits are, border classes are. And a very interesting result came in 2020 by Mrinal. Mrinal showed that forget about K, large K, even Fanin 2 depth 3 circuits are universal. That means any polynomial P can be written as sigma pi sigma bar with Fanin 2. Now, I just want you to absorb this. If you have not seen this, this is a very peculiar and a very strong result. So if you recall the classical version, I know there without border, I know there are polynomials such that it can never be written as sigma 2 pi sigma, no matter how your large d is. But I am saying, if you allow border, if you allow this kind of notion, then any polynomial p can be written as in the border where of course the proof actually, if you look at the proof, the D was exponential. But anyway, you can still write it. So that means these sigma 2 pi sigma circuits are universal. Any polynomial, so these border class, even with Fanon 2 depth 3 circuits, are universal. Any polynomial can be written as that. Okay, so now let me quickly go through that. So the debordering, what do you mean by debordering sigma pi sigma circuits? So remember, this proof required D to be exponential, right? Exponential in N and D. Not required, but the proof, if you start with arbitrarily P, your D will be actually exponential. But now let's just restrict ourselves to polynomial size circuits. That means I want to understand sigma pi sigma approximations, that means bar, sigma pi sigma bar, but my D should be polynomial. Otherwise, exponential size circuits and so on, it is, we want to understand only when the circuit size is polynomially bounded. That means your D is polynomial in N. I want to understand what is the class, what is the bar class of this. Okay. The question is it even explicit? Is it even computing some polynomials where the coefficients are explicit? Is it even inside VNP? This was also not clear, even if you restrict your D to be poly in N. And now I state our result. So what we showed is that this bar class sigma 2 pi sigma bar is inside VVP when the size is polynomial. In particular, if you start with Fanon 2 depth 3 circuits and border, that means you are that there is a polynomial which can be approximated by a Fanon 2 depth 3 circuit, a polynomial size. It can be exactly computed by a projection of determinant, because remember VPP was determinant projection. Okay, so this is the result we proved. Definitely I will not go into the details, but yeah, so you can replace this 2 by any arbitrary constant k, the same results holds. Although the determinant size, it is poly, but it is like the k will come, but as long as k is constant, it won't matter. But it is really large. It is like s to the exponential in k. That essentially we show that the dimension is s to the exponential in k, but as long as k is large, k is constant, it is poly s. Okay, so this is the theorem. This is the result we prove. I'll just conclude that. But any questions? What we proved and what? So again, just to reiterate, Minal showed that if you do not restrict your D, it can be arbitrarily large, exponentially large, and so on. Then any polynomial can be written inside this. But we want to understand when D is polynomially bounded. That means polynomial size circuits. What are the polynomials that are approximated by polynomial size depth 3 Fanon 2 circuits? And we claim that this is easy. It is not just explicit, this is easy, very easy. It has a small determinant. Okay.
So can I extend this to say if k is log, so if I take k to be small of log,
right, then still it is, then you still have a sub-exponential.
So as in like, so it is, so you have a sub-exponential, sorry, sub-quasi-polynomial projection of the determinant.
Right, yes.
So, and VP is a class where you have quasi-polynomial projections of determinant.
Projections of, yes.
So if you go for like k, which is small of log, you're still under VP.
Still under VP, yes, exactly.
Yeah.
But as long as, once you go to log s, it's not clear.
Yeah, so as long as you're small of log.
Right, small of log, it is, you are right. It is still, you are still inside that. Yeah. Correct. Yeah. So so this is the result we showed, and there are some bunch of other PIT results and so on, but I don't want to define this PIT and what, but we also have some PIT results for these classes. But so I want to conclude that. So the first conclusion, the first question is that, what we showed is that this class is inside VVP, right? we showed that sigma k pi sigma when D is poly bar is inside VVP. Of course, the question is, can we separate that? And in fact, we actually separated that as well in a subsequent work. We in fact showed something like there are polynomials which can be computed in k+1 fanin bar, but cannot be computed. Okay, but if you want to compute this as fanin k, it requires exponential size. And this will also prove, I mean, the similar result will also prove the not equal to VVP and so on. So this separation is also now known. So we now know that this bar class is strictly inside VVP for D equal to poly n. Okay. And as I was saying that we can also talk about heating sets for these classes. If you just a remark, if you remove this border, there is no border, then the classical circuits has polynomial size heating sets known. In the border that fails, but you can come up with quasipolynomial-time heating sets. Of course, the question is, can you do something? I mean, improve it to polynomial, and of course, I mean, this is just depth 3. The other question is that can we extend this result or this technique to depth 4 or depth 5 circuits and so on? This we could not do. We could do in some restricted way, but these are very restricted circuits. So it's all these depth 4 circuits and so on and so forth are open. And another question I did not mention, but yeah, the other point would be to actually show that this is inside VF. Okay, you could have asked that whether this is inside VF or not, and yeah, that is not clear. I mean, can you improve this VVP to VF instead of saying that it has a small determinant? Can we show that it has a small formula? That is still not clear to us. So yeah.
Pranjal,
Right.
question. If I remember correctly, this polynomial which is in k+1 fanin,
Right.
that has a small formulas, right?
Right. So you can separate VF. So I'm not saying that separation. I'm saying that inside VF.
Right, right.
Separation is known, but
right.
But
So,
that does not mean that it. I mean, I'm saying that
Yeah, it doesn't mean that it's contained in formulas, but yeah.
Right. Yes.
But you can definitely show that there is something in formula which is not computable here.
Exactly. That. So separation is clear. My question is that can we now do give a better debordering result? That means take a containment. Exactly. So instead of determinant, can I push it down to formula?
Right. And one more thing. This hierarchy that you get until VVP.
Right.
Another thing that is not known, I guess, so it doesn't follow, is that the union over k from 1 to infinity, that is not contained in VVP.
Actually, k has to be, let's say, I don't know, k has to be poly n or something like that, right? For that, otherwise it does not make sense. Because if your k is really large.
So what I'm saying is, no, but k is still constant. What I'm saying is that there is not a single, means you don't have a single polynomial which is
right, no. But if you can talk about imminent. I mean, in our paper we talk about imminent.
Imminent or IMM?
Sorry, imminent. IMM, iterative matrix multiplication. And but you are saying that you do not want to fix your key. I see.
Yeah. So it's a single polynomial that works against all constant.
Right. Maybe you are right. That we do not. No, but does not it follow? Because
so how does it follow?
Yeah. So what I'm trying to say, because my key is constant, right? So so what I'm saying that let's take let's say determinant. Okay, to that. Okay, even if you take determinant, the problem is that no, but the same proof actually will go if you take determinant, just determinant.
Okay, how?
I mean, just symbolic determinant. because essentially you want to show the same thing that so I want to show that determinant cannot be computed by sigma pi sigma for constant k. That proof will also go, because essentially that proof, the symbolic determinant I meant.
You can show that it cannot be approximated within polynomial for any constant.
For any constant. Now that does not require any k to define determinant, right? So that actually now goes through.
How do you show this? Is it through the classical lower bound?
The similar proof that we did. I mean, you have to go through almost the similar proof, but ultimately you will ultimately get that. So eventually you will show that some projection of determinant has some large partial derivative, which will also go through. I mean, that you can also show.
I see. Okay. Yeah, you can use determinant now to separate the union from the VPP.
Right. Yes.
Yeah, that looks feasible. Yeah. Nice.
Yeah.
Thanks. Sorry.
No, that's fine. That's a good question.
Contain capital D here in the.
Sorry.
So here you mentioned like small d and capital D in the first statement, right? In the.
Yeah. Right.
So how are small d and capital D related? Capital D can be anything.
So actually, really, I mean, capital D can be. I mean, here actually, we are really saying that capital D should be like 2 to the omega and something like that. And D is like poly in an order, I mean, whatever you can say. But yeah. So actually, I just wanted to. I mean, actually, if you look at our paper, we really do not talk about pi D. I mean, this product fanin can also be different for different. I mean, this is non-homogeneous. So you can just talk about sigma k plus 1 pi sigma without going to D. But then I had to define this DI and so on. People could have get confused. So that's why I just wrote. But yeah, you can just forget this D and capital D and so on.
Makes sense.
But then I have to,
So also there is this thing which you mentioned about like not many polynomials having many symmetries. So basically very few polynomials are characterized by symmetries.
So for example, I can tell you one example. I mean, maybe for determinant actually it is very easy to state. So that's why I say. So or easy. I mean, in some sense, is relatively easy to do. So look at all the polynomials if, let's say, such that I have this. So let's say I have determinant A, B, not determinant. I have matrices A, B, and some symbolic polynomial X, some symbolic matrix X. Okay. So let's try to come up with all the polynomials f such that f of AXB equal to f of x, where your determinant AB equal to 1, determinant of A dot B equal to 1, or determinant of A equal to 1 by determinant of B. You can show that determinant is a constant multiple of determinant is the only homogeneous function f that could actually satisfy this property. There is no other function. So this is a symmetry characterization, because f AXB equal to fx is like a symmetry, because it is like a stabilizer of that.
Right.
So this is a very easy symmetry characterization. But for arbitrary polynomials, you cannot just state those kind of symmetry and say that, okay, I mean, this is a symmetric characterization of that. So very few functions can be like that kind, uniquely determined by.
Things are well characterized, but they're easy polynomials anyway.
Right. Exactly.
Pranjal, I had one more question. So you, though you didn't presented your proof here, I wanted to understand. So when you do deborder, right? How do you take care of the possibly large degrees of epsilons? Where does it? How does it taken care of in the proof? Sorry, I haven't read your paper also properly. So
no, that's fine. Let me say how to be non-technical and technical at the board. So the point is, okay, let me tell you one intuition that actually works. So let's say I have two. Okay, so this is an abstract question. Let's say I have two classes, C and D. Okay. And suppose I know how to deborder C. That means I know what is C bar and I know what is D bar. I am claiming that I know how to deborder C bar dot D, C dot D whole bar. So C dot D you can define, right? As a circuit complexity class, you can define C dot D. That means just you are taking all F belongs to S, C, G belongs to D, F dot G. All these polynomials. This is from C dot D. Now you want to deborder C dot D bar. Now I am claiming that C dot D whole bar is actually C bar dot D bar. So that means if you can individually deborder C and D, you can deborder the product. So now why am I saying this? So now why am I saying this? Now let me come to that. Eventually our proof method shows that there are things you can do. Let's not get into that. Ultimately such that you will eventually have a pi sigma circuit. So it will be like a pi sigma times a sigma with sigma or border warning, a sigma with sigma bar. So pi sigma times sigma with sigma bar. And you really want to understand the deborder of that. So pi sigma bar is understandable because it's pi sigma. Sigma with sigma bar is understandable. This is ROABP or ABP, small ABP. So that means we know really the product. So that is that that's otherwise I have to be really technical. But that is
good.
So this is one point, and also another point in the sigma with sigma bar or the depth diagonal bar. Even if there could be actually large epsilon powers, but it does not matter since we use this Nissan's characterization. So sigma with sigma has a small ROABP, right?
You use the non-commutative closed.
So sigma with sigma bar has ROABP bar, and now ROABP bar is ROABP because of Nissan's. So it does not care about epsilon powers. So then your epsilon power is does not matter. In the pi sigma, that means product of linear polynomials. Again, epsilon power does not matter. Whatever that you can just take it out, and so your epsilon powers really does not matter in the proof.
Right. I see.
So where here are you using the pi sigma? Like I understand sigma for sigma, but like where are you using this pi sigma?
No, because if you remember, I mean, if you go through the proof, we divided by T2, then we deborder.
Got it.
But then you have to product multiply T2, right, or something like that. Otherwise, you will. Yeah. So T2 is like product of linear. So yeah.
Yes. So I'll stop recording for now. Yeah,